I'm Ian Paxton, and today I'll be talking about the unimolecular elimination reaction, or the E1 mechanism. So the E1 mechanism is very similar to the SN1 mechanism in that they both follow a similar rate law, where rate is equal to K times whatever substrate you have. And yeah, similar to most SN1 reactions, it's the second step where it will define itself, but it starts with the electrophile leaving, as it's going to attract the electrons from this bond to itself, forming a carbocation in the process. Now, because this is a non-concerted reaction, and this is going to form in multiple steps, we do risk rearrangement here, and so as a secondary carbocation is less stable than a tertiary carbocation, we will likely form through a methyl shift tertiary carbocation in this example. We'll be coming back to this later to explain the difference between Zaitsev and Hoffman, but to start with, what we'll get as a result from the methyl shift is this, and from here, one of the hydrogens from this will be removed with our solvent, which for example could be methyl. Remove one of the hydrogens. Now, the hydrogen removed, electrons attaching hydrogen removed will go to the adjacent carbon-carbon bond, which will then form a double bond, pi bond. Now, assuming no rearrangement takes place, and we have something like this, where you're going to get two different products, depending on which hydrogen is removed will depend on the product itself. If the hydrogen is removed from this carbon, then we will have a primary alkene. If the hydrogen is removed from this carbon, we will have a secondary. Now, this one is referred to as the Hoffman, and this as the Zaitsev, or Zaitsev, depending on your pronunciation. And E1 mechanisms will always follow what is known as Zaitsev rule, as described by Wade, and that is that the Zaitsev product will always be the major product in a E1 reaction, with the Hoffman being minor. And unfortunately, E1 reactions have a major flaw to them, and that is because they're so similar to SN1 reactions, they in fact compete with the SN1 mechanism. So, going off from here, it could be possible that instead of attacking our hydrogen, our solvent instead act as a nucleophile and attack carbocation instead, forming this intermediate. Now, just like this step, additional amounts of the solvent will remove the excess hydrogen, forming an ether. And this can be useful in a sense that you might be able to use the difference in boiling points between the alkenes and the ether to remove one from the solution if you desire the other. But it still remains a major issue with this mechanism. Now we'll do a quick sample plot. display this. So for our sample problem, we'll be working with 1-bromo, 1-methyl cyclohexane, which will look something like this. And the three products that will form when it is heated in ethyl alcohol. So we're going to form three products as a result of this. Now, as we previously discussed, first thing that's going to happen is our leaving group is going to leave salt from electronegativity, forming our tertiary carbocation. And again, this is where it's going to distinguish itself from the SN1 mechanism and compete with the SN1 mechanism, as we can have the ethyl alcohol remove hydrogen from here and form this alkene. We can have the hydrogen remove a hydrogen from here or here, this alkene. Or, again, we could undergo an SN1 mechanism and form an ether. And so these three are going to form. Now, of the alkenes, again, going back to Zaitsev rule, as this is the more substituted product, this will be the major forming product, and this will be the minor, at least in respect to these two. Now, in regards to health and wellness, the E1 mechanism is not mentioned fairly often, but it is used in the production of certain cancer drugs, such as coumarin derivatives, by which sulfamic acid is removed from the following structure. Bear with me, as it is quite large. Due to the electronegativity of this atom and the electron pull by sulfur and the electronegativity of sulfur, as well as the stability of the resonance of this structure itself, these electrons will easily move onto this oxygen, removing sulfamic acid and allowing us to use this compound, as this forms a carbocation at the end result, which will allow us to form the necessary cancer drug.